this is the Voronoi region for S1. This is the Voronoi region for S2. This is the Voronoi region for S3. So my decision device will figure out, given any point in this two-dimensional space. So it takes a two-dimensional variable, or excuse me, it takes two real numbers, and each of these are coordinates in space of the true signal plus noise. And what it's going to do is it's going to map, if this point lies in the Voronoi region for any particular point, it's going to decide that signal was sent, the corresponding signal was sent. So in other words, if my signal lands in there, I'm going to decide S0. If my signal lands in here, I'm going to decide S1. If my signal lands in here, I'm going to decide S3 and so on. So you could write that mathematically. You don't need to. This is a nice geometric interpretation, but mathematically, here's what you do. So if I have a vector A, excuse me, if I have a point in space A and a point in space B, where these are ordered pairs. To find the distance between those 2 points, what I can do is I can take the norm of A minus B. So algorithmically, so this is the geometric interpretation, but algorithmically what I do is I say, take the norm of, let's let phi x be the filter output in the sx direction, and phi y be the filter output in the sy direction. So in other words, one at this point would, for example, be phi x, phi y. This might be, let's say, x is, let's say, 2, and y is, let's say, 5 or something. So what I do is I take the difference between this ordered pair, phi x, phi y, and each of the signal points. So this would be phi x minus alpha I, comma, phi y minus beta I. I take that distance. So that's for S0, that's this distance. For S1, it's this distance. Oops. For S2, it's this distance. For S3, it's this distance. I take all those distances and I find the minimum. So I just put my decision device, or my decision is the min over all I of that, but I don't care about the value, I don't care what the distance is, I just care about the value of I that minimizes it. So to pull off that, I use this arg min notation that I mentioned before. Where, just to remind you, min I would be the minimum distance, but arg min is the value of I that minimizes this.
Sir,
yes.
For the previous example that we did like Si is equal to alpha and beta I, right?
Yes.
So what would be the filter output for that Sx? Would that be alpha I in that previous example? Like filter output, is it, this is before going into the decision filter or after?
It's before. So this is what the decision device is doing. So Si, the noise-free filter outputs, are alpha I, beta I. It's the coordinates of each signal in signal space.
Yeah.
And basically I'm looking at the distance between the filter outputs, phi x and phi y, and those coordinates alpha and beta I. So I look at that for each I. I don't know in advance which one was sent, so I look at that for each I and pick them in. Yeah?
Is there a side effect to moving up in signal space? Like higher dimension?
Complexity is one. Sorry?
You can extend vectors to like n spaces, right? So
yeah, so there's where we're going towards is there's a natural reason why we talk about two-dimensional signal space. It is very possible to extend this to n dimensions, and actually there are a lot of benefits to that. The downside tends to be complexity. So, for instance, if everything's nice and rectangular, then these Voronoi regions are really easy to deal with. But unfortunately, if they're rectangular, you don't get all the benefits of signal space. So where you tend to get the benefits of very high dimensional signal space is when you have sphere packing. So all your signals are at the center of a sphere, and you try to pack them as much as possible. If you're packing them as much as possible, the amount of energy you're expending is generally, let's say the origin is here. The amount of energy you're expending is proportional to your distance from the origin. So if you pack these all in, you have less energy output. So it turns out that if you have an enormous high dimensional signal space, it turns out you can pack those spheres in like 30 dimensions, 40 dimensions, 50 dimensions, extremely compactly. The problem is, what are these Voronoi regions? Well, in 2 dimensions, they're hexagons. In 3 dimensions, it's not even possible to visualize what they are. I mean, it's some weird polygon. 4 dimensions, I mean, forget it. So, one major problem with these kinds of things is that finding the Voronoi region and optimally trying to detect which signal was sent is ludicrously complicated. But we are not going to go beyond 2 dimensions. The application that we're going to talk about is when, and we're going to get to that actually more likely next class, is when you apply a carrier frequency to your signal. Basically what that means is you're multiplying it by a sinusoid. When you multiply it by a sinusoid, you have the choice of multiplying it by cos or by sine. But it turns out that cos and sine are orthogonal to each other. So you can use cos as a basis vector and sine as a basis vector, and you get this automatic 2-dimensional vector space. But we will talk about that more next time. What I want to mention briefly right now is probability of error.